So I'm the chief system architect of SiteGround. We are a hosting company, but what I'm going to present today is not anything that is directly connected to a company and nothing that actually we use in production right now. I'm organizing the biggest open source conference in Bulgaria, around 3,000 attendees. And since I'm a very big open source fan, this is why we will be playing open source games today. So the talk is about comparison of eBPF, XDP, and DPDK. Who here doesn't know any of those three things? Perfect. I hope you understand a few ideas around them. So I will compare what I will explain to you what I have done this year, because in January I decided that I want to do this for our company, or at least to have it as an open source project. So why do we need to compare these things? Because currently DDoS attacks and those attacks, floods, are a big issue. For our company, we have a lot of attacks. For me, this is a lot. And some of these attacks cannot be easily mitigated. So the pattern is slowing down because we are handling them better these days, but still 31 attacks resulted in service disruption for our company, for our customers, which is a big problem for us. And I wanted to solve this problem. The problem there is that you can solve this problem only with big hardware, and I'll explain this a little bit. But the attacks are sometimes very easy. 20,000 packets per second, and you get 30 cores down from one server. That's a big, big issue. The server can handle this, but 20,000 packets I can generate on a normal laptop, maybe even on a phone. So this is a problem. Everyone can generate this attack and bring down 30 CPU cores. And there are scripts to do this, so script kiddies, children can do this to you and disrupt your service, which is a big, big issue. So buying additional bandwidth usually solves the problem of receiving the attack. Then after you receive the attack, you need to scrub the traffic and allow only clear traffic that's supposed to reach your server, reach your servers. At this point, things become very expensive. Otherwise, if you don't want to handle this traffic at all, you offload to services like Cloudflare. And I'll explain why this is no go for some companies like ours. So first, let's decide to invest in hardware and bandwidth. The problem is that our company has 8 different locations worldwide, different data centers, and not every data center is okay with investing a few $1 million for a device that would be used only by us. Or if they have invested in this device is shared by other customers also, which is a problem because you cannot use a dedicated 10 gigabit or 40 gigabit port. And the problem is that these devices, they are not 100 gigabits, most of them. They're 10, multiple of 10 to 40 or 50 gigabits, but 100 gigabit is extremely rare, even in very expensive data centers. So if the attack is larger than the capacity of this device, what happens is that the attack results in no routing the attacked IP. Again, service disruption for the customers. The other problem is that even if you can handle the traffic, sometimes this disrupts the connectivity in your rack or the whole row of racks. So because it's maybe 200 gigabit attack to your servers, what's happening is you get 200 gigabits to the edge switches, but this overflows the uplinks of the edge switches, so you don't get the traffic to the rack. So you have to solve this somewhere, somehow. You can completely move out this traffic of your network by going, for example, with Cloudflare, but there are other companies also. You can point your DNS to them, and they will receive all the traffic and clear the traffic. Only valid traffic will reach your servers. Controlling your DNS at this point becomes a problem because you now have to configure it via APIs. And if you have 1 or 2 domains, that's not a big issue. But we are a hosting company. We have millions of domains. Bulk actions on these APIs usually take a lot of time. So now, instead of using a set command on a few servers or a few hundred servers and fixing stuff for us, changing something, now we have to wait for an API call to finish and hope it actually finished. So this is not suitable for large hosting companies like ours. So what we decided to do is, let's build a VM. Why VM? Because I can deploy a VM in Amazon, I can deploy a VM in Google, I can deploy VM in Alibaba, or whatever I have that supports a VM. So I can scrub traffic everywhere. If I make it on hardware, it will work. Unfortunately, I would need specific hardware, and I'll talk about this in a bit. So what I wanted was at least 10 gigabits bandwidth per VM and at least 8 million packets per second scrubbing power for this VM. And I want to do that in Linux, which is fine if you know what you're doing. Scrubbing UDP, DNS, and NTP traffic was the most important part for me because I don't have any other services running on UDP. Then scrubbing TCP traffic with sync cookies was also important because I wanted to scrub the traffic on the filter, not on the servers themselves. Because the servers may have only 10 gigabits, while the VMs can be multiple of 10 gigabits. And wishful thinking is caching the HTTP responses. We are still thinking about this. So the problem is the Linux networking stack. In general, it looks like this. We'll focus only on the part that is forwarding, so this thing here. And this is the general picture of the networking stack. Actually, this is the networking stack of Linux. Your packet starts here, here, and then it traverses all this line here for the whole packet to go out of your machine. Please, if you have questions, ask them immediately. Stop me immediately and ask questions so I can respond with the proper slide immediately, okay? Don't be shy. So what we are going to focus on is this one here, which is this thing here. So you have a packet that is received. Then you go into your driver, and there you have XDP that can be combined with eBPF programs, and then you're allocating the SKB for the network stack onwards. At this point, you're at least around 20, 22 cycles. So after this point, there are a lot of cycles happening here. So everything from here on is slow, and slow as hell. I will be going back to this picture a few times. I'm sorry. You would understand why. So in 2019, Cloudflare had this very nice article about how to drop 10 million packets, which is very nice, and I confirmed their results and actually used their slides here in my presentation because I didn't have time to, again, get the numbers from my home lab. So IP tables can drop around 2 million packets per second. The note here is this can be done with only a single row in the pre-routing chain. If you add more rows, immediately you see degradation of this performance. And 2 million packets per second, it seems large, but when you have a DDoS, 2 million packets per second is small. So if you configure your network in a way that you can receive all this traffic on your end nodes and the hosting machines, you would be able to drop at max 2 million packets with only one row. But what would be that row? Would it be the /24 that is attacking you, the /12 that is attacking you? What would you put there? Having multiple entries is a problem simply because in this picture here, you are in this forward filter here. So you have, in this pre-routing filter here, you have already done contract. And this here costs a few cycles. I don't remember how many, but it's not cheap. Even if you decide to use IPsec, who here knows IPsec? For the rest of us, for the rest of you, sorry, it is a way to put hashes or arrays of IPs or prefixes directly into a single row in IP tables. So you can skip the whole problematic accounting of IP tables and going through all the rules in IP tables. Instead of having maybe 40,000 rules in one chain, you now have one rule that is matching all of these prefixes here. That is very nice. There are different ways, different things in IPsec, but generally this is the idea. So even with IPsec, it's again slow. So how slow? This is from the Cloudflare blog post. What if you're dropping with IP tables in pre-routing? Here you have 1.6 million packets per second, and if you're doing this with NF tables, I still don't know why NF tables is slower. It's supposed to be faster. And what if you're using traffic control, TC, to drop the packets? You can see that with TC you can reach around 2 million packets per second. Yes?
That's TC with IPsec?
That is, the question is that TC with IPsec? No. This is TC directly with drop. No eBPF here, simply traffic control has U32 filter. U32 filter, okay? And then here is what's happening when you have XDP here. This is simply because you're dropping already here and not going through this chain. This is why it's so fast. So even though I knew these results, I decided to, the demo code of Cloudflare is here. I have links on at the end of the presentation that you can go through. So even though I knew about XDP, I decided to be a very smart ass and to write an IP tables module to fix my problem. Why a new IP tables module? Because I wanted to do layer 7 deep packet inspection. I wanted to get into the UDP packet and check the domain names that were there and the actual requests that people were doing. Doing this with the IP tables modules that currently are available is very, very expensive. With those, I could do maybe 50, 60,000 packets per second, which was very bad. I managed to make it around 260, 280,000 packets per second with my custom IP tables module, but this again is too small for larger attacks. So I want to do something better, and I decided that I'll use eBPF. Who here knows eBPF? Okay. Extended Berkeley packet filter is a way to talk to the kernel in different ways. So you can either trace different processes or parts of the kernel, or in our case here, load a program that will drop packets from the network. You have access to kernel functions, and you can do some limited actions there. The eBPF programs are small programs that have to have a way to finish. It's not possible to have endless loops inside them. So they're fast and proved that they will finish. So you load those into the kernel, and they do some stuff for you. There is a nice presentation from Daniel Berkman from FOSS 2016. I was on that presentation, so I was, okay, I know eBPF, I'll do that. And I implemented what I did with the IP tables module in eBPF. This is now eBPF that is attached via traffic control. So TC eBPF. I managed to do 350,000 packets per second, but nothing more than that. And this was with 2,000 domains in the eBPF map that I used for comparing the traffic. If I used one, I don't remember, but I think it was around 1 million that I managed to make. And in order to get these results, you have to pin your NICs to certain CPUs, and you have to have your user space software not using those CPUs. So CPU affinity and CPU sets were very important in order to make it faster, which is a problem in cloud environments where you don't know if these CPUs are actually dedicated to you. Because the virtual machine gets something, but what it is, you don't know. So after that, yes?
Can you return, please?
Yes?
What do you mean by no checksums?
I mean that what I did when I was inspecting the packets was I didn't do the UDP checksum at all. I was hoping that the packet would be correct. This can be fixed with offloading the UDP checksum checks, but I haven't tested this. So I was simply hoping for the best during my tests. It has to have UDP checksums, otherwise you have to have more checks from the data when you are inspecting the packet contents. This is a problem if it is broken, right? So, yes? What is the performance degradation if we enable checksums? I don't know because I didn't implement it. Sorry. But it would be at least, give me a sec, maybe around 20 cycles. It can be less, depending on how you implement it, because if you implement it with AVX instructions, which is a hacky hacky instrumentation, you can do it in maybe 10 cycles, but I'm not sure. It depends. And this is cycles per packet, right? Other questions? Okay. So then I decided, okay, I know something that is even faster than eBPF, and it's called DPDK, Data Plane Development Kit. It's very nice. A few years ago, Intel decided that Linux networking is slow, which it is. So they decided to make it faster by simply skipping all the network. Sorry. They're plugging in here and directly going to the application itself. So you can either connect an application to the network card or virtual machine to the network card, which allows you to be very fast. You skip all of these things here, and you create a data plane that is forwarding all of your traffic directly to the NIC and out of your machine, or from the NIC directly to your application. So at that point, I knew that I had to order a few NICs, so I ordered one Intel and one Solarflare, and I'll explain myself for this. With both of them, I managed to drop everything that I put on the wire to the card. Everything that was below the 10 gigabit limit of the port itself. I haven't tested with the 4 gigabit NICs, 40 gigabit NICs. I'm sorry. Again, I didn't have the time to prepare my test lab at home. So the Solarflare has a very nice addition that you can upload code to this card. Please don't ask me how, because I cannot tell you on the microphone. Sorry for this. So DPDK was nice. You write C code. It's for me understandable, but it has the complexities of strange network architecture that you have to use now and strange functions for this, which became a problem in my team. When I shared my idea with them, they were like, DPDK what? New networking? No, this is not very good. So they didn't want to participate in supporting DPDK at all. Also, DPDK required specific hardware, which was a problem for me because I don't know if I would be able to buy this hardware in every data center in the world. Especially, for example, in Amazon and Google, you don't know what hardware you run on for the networking, I mean. So I wanted to have something that works better. But I had a talk with a friend of mine, Marian Marinov, and he told me, you know, if your team is scared about DPDK, you can write it in P4. And I was like, what the hell is P4? This is another programming language that you can use to actually build DPDK programs. Which was nice. It allowed me to easily update the logic and also update the content of the DPDK programs. Unfortunately, again, my guys said, P4 what? So no, we didn't go this way. I simply tested it. It worked fine, but it requires a lot more time to change anything in your program, and testing it is more like putting it live and testing that. I don't know, I'm not an expert in DPDK, so I really don't know how to properly debug the DPDK programs. So this was a problem that everyone in my team agreed we should avoid. Then we ended up using XDP because obviously it works. So it's here, it's fast, it's the same way that DPDK does its work, but it can be transparent for the user applications, and you can use the fast path of the networking as much as possible. So it's also supported by many drivers now. It was implemented by Jasper Brouwer, and when I asked him a month ago at Linux Pumpers about this, and he said, I implemented it simply because the DPDK guys told me that it cannot be done in Linux. So I'm really happy that Jasper took that challenge and made XDP. 2 years ago, it was only available for a few drivers. Now, most of the drivers in the Linux kernel support XDP. So it can be a single application that you're installing there, or it can be combined with eBPF programs that can extend the functionality you want. So what I did was I created a filter similar to the one you see in the code demo of Cloudflare, and this filter, instead of having a single prefix there, it used an eBPF map that would when a packet arrives, you would first check the IPs the IP that it's arriving from with a map, and then the second thing is to execute the to extract the actual data from the packet and compare the data. In my case, the domains, the host names that are requested, compare that with host names that are entered in the map itself. After that, it was needed. I needed a tool that can update the BPF map from the user space. So eBPF requires two things. You need a program that is loaded inside the kernel to actually work there, and you need a user space tool that would talk to a file descriptor directly to this eBPF map. So the kernel and the user space tools share only this, let's say, memory range in the kernel, which is the eBPF map, and that's the only thing they share. So the user space tool is used to load or delete host names from the map, so I can update on the fly what I have in the kernel filter. So after I had the user space tool, I actually had a UDP filter, and this was all that I needed. So the setup for this VM is pretty simple. You have an IPv4 IP address that is under attack. You move this IPv4 address, you route it to the VM itself that is filtering your traffic. Announce it from there via BGP, for example, in my case. And then all the traffic from your routers to this IP goes to this VM. After that, at this VM, you simply add routing for this IP, static route, to the machine that actually hosts this IP. So you filter on this VM, and the traffic, the clear traffic, goes directly to your machine. It's pretty simple. You need, I had 2 shell scripts to do this for me. One to move the IP on the machine, and one to create the routing back. So this is only incoming filter, not outgoing filter. At least in my case, I really don't need an outgoing filter. So now, yes?
What kind of map do you use?
eBPF map array.
Map array?
Map array, yeah.
Size?
It depends. First, I started with a very small size that was capable of getting only 64 entries there. Now,
domain names?
yes, in order to get 2,000 domain names, I required actually 4 maps at the moment. So 512 at the moment. I could do it with a single map, but if you experiment a bit with the eBPF, you would see that you can actually bind the maps to particular CPUs. So I want to separate the maps between CPUs, and when I have, for example, 12 or 24 cores, I want to be able to use all of these cores. So I was setting the CPUs to be used, the map that I'm using, to use only 4 CPUs, then the other map, the other 4 CPUs. This way I would get better performance out of it, instead of getting a single one, because when you're going through a single one, all of the CPUs have to agree for that. When you're going, now I'm limiting the number of CPUs that have to agree that you get this data. Why don't I use the per CPU map? Because then I would need to go per CPU for... I would have one large that I would have to copy for each CPU.
Yeah, exactly. But the size is so small.
No, if you have 2,000 entries, you would have...
Okay. Oh, you said 64.
Yes. It depends on the size of the map you want to have. If you want to have bigger maps, you have to separate them. If you have smaller maps, it's fine. So the idea was the UDP scrubber is pretty simple. You simply get the data from the packet. If it matches something from the map, and by something I mean the TOD and the host name after that. I don't care for subdomains, whatever is after that. So the first part after the TOD and the domain. And there, I know that there are TODs like .co.uk and stuff like this. I have a pretty simple hackery there that says, okay, the TOD is everything that starts with the first 6 symbols to the point. So that was just a little bit tricky when I started scrubbing the traffic. And the next thing I really want to do is have caching for each response with TTL. This would allow me to filter directly all the traffic that is going to the DNS server on the hosting machine. One interesting thing here is that if you get only proxy, so caching for the DNS requests, you actually get, you don't filter all the traffic from attacks. If I create traffic that is random source ports, random source IPs, and random host names, all this traffic will hit the DNS server because it's not cached. It cannot be cached because it's random, right? So the only thing is, the better approach for me was to simply filter the requests if they're going to something that is hosted on that IP. If it's not hosted on that IP, I shouldn't let it go. Then the TCP scrubber, I haven't done this at all because 2 months ago I had to stop on working on this project. The idea is pretty simple. You need to match the destination port, and if it is not in the allowed list, you drop the packets, SYN packets with that destination port. Everything else has to have SYN cookies. Here is a problematic part when you have multiple VMs of this. You have to synchronize the SYN cookies between these servers, so you have to use a hash that is predictable for this. And also, if you want to be able to do contract, you have to share the contract state between these servers. Again, this is easily done, but it's not implemented. The idea was that most of the DDoS attacks that were SYN floods, that were TCP, were SYN floods, and so TCP SYN cookies should be okay. And then, if you stop the first SYN, you actually have to retry that SYN packet again to the server that had to receive that one. Testing this setup was a problem because generating so many packets is not something that you see that you can do, for example, with Pink or whatever tool you have. So you have to use the kernel packet generator, but it has its limits. So last month I talked with Jasper, as I told you, at Linux Pumpers, and he told me that he has a patched version of packet gen that there is a link at the end of the slides for this, that can generate a lot more than 10 million packets per second if you have more than 10 gigabit interface, which was very nice. I also patched that to because it's working with UDP only, so I also patched that to generate TCP packets for the TCP SYN flood. Now, how to get from 10 gigabit VM to 200 gigabits? It's pretty simple. You use equal cost multipath on your routers, and you're all set. I did that on my switch directly because my test WAP is with 40 gigabit uplinks, and the switch that I'm using has BGP support, so I simply used ECMP there directly to the machines that I was using. And any questions, these are only the links. You would see them in the presentation. So, questions?
Okay, thank you very much for the presentation. Before we start with the questions, I forgot to mention we have some prizes for the best question, and it's up to you to pick one. You have the cups and the thermo cups. I just want to say that Dmitry, it's ideal if it will be not Dmitry because he's working in our company.
Okay.
Okay, so actually, guys, please raise your hand if you have any questions, and if you somehow shy to ask this in English, I can translate this for Russian. Если по-английски не очень, мы с удовольствием переведем. The first question.
Can we use not VM and real hardware?
Yeah, you can use real hardware. You would get even better performance there because you would not use the virtual net. One important thing that I didn't mention was that if you're using VMs, you would definitely use virtual net driver, not anything emulated there. Okay, with the hardware, it would be faster. It would be better. But you would have to have the dedicated hardware sitting around for this, which is not everyone keeps like 40 core machines with 2 or 4 10 gigabit interfaces idle.
Okay, thank you.
Could you say which kind of real DDoS attacks did you test? For example, about packet fragmentation or broken packets, and what about productivity in kernel bypass tracks? And which measurements did you do about this case in these cases? Thank you.
So in our case, in most data centers, we don't handle our own networking. Usually this is done by the data center provider. So when we get attacks that are more than 10 gigabits that cannot reach our network interfaces because the machines have single, they have 2 different NICs, but one is private, one public, and one public 10 gigabit interface is the only thing that we have. So if we get attack that is more than 10 gigabits, we cannot measure that. We rely on the ISPs to actually tell us how many gigabits the attacks were. This was one of the reasons that I really want to make our own filter so we can get the networking in the data center to our own equipment and actually measure these things. The attacks that we get usually are UDP floods, and a lot of the times these are UDP floods to ports that we don't have services on, which is plain stupid. You can drop all of this with a few lines of eBPF and never worry about this at all. Like having a firewall before the firewall on your machine, that is 1,000 times faster than your firewall. The next biggest thing is TCP SYN floods, and the last thing is actual HTTP requests from devices over the internet. For the last thing, what we are doing is usually there is a pattern in the requests that they are making. So we are getting this pattern as a pattern in the text of the HTTP protocol, and we are dropping that on the web servers themselves. However, when the attack is more than 5-6 gigabits per second, these servers are not they cannot handle the traffic. So what we are doing usually is creating an array of web servers that have equal cost multipath between them and push the traffic between those, and after that to the actual web server. Then we are filtering with actual Nginx web servers.
Okay, so thank you very much. I think that we run out of the time for the session, and I suggest you to continue discussion in the discussion zone after that.
Okay.
What's the best question? Okay, you need to think. It's a nice cup.
The first guy, I don't know. Sorry.
Okay.
Yeah.
For you. Okay, so thank you very much.